Good day, this is Mark Marin Magbo, and today we'll be discussing an introduction to membrane technology for chemical engineers. Our learning objectives for this lecture is first, to understand the definition of a membrane and the interconnection of membrane science with chemical engineering. Second, to gain an overview of the transport phenomena behind membrane separation as a unit operation. And third, to appreciate membrane separation processes through their various industrial applications and their significance to some notable chemical engineering problems. First of all, what is a membrane? We can define a membrane as a distinct, thin, semi-permeable barrier which retains specific components while allowing others to pass through according to the certain properties to which it is selective. So, you might be curious and you might ask, is it different from a filter? Or the membrane is the same as the filter? The answer is both a no and a yes. No, it is not different because in actual, many things are both a membrane and a filter. We can actually say that all membranes are filtered. However, we can also say that yes, they are different. A membrane is different from a filter because not all filters are membranes. For instance, a mechanical sieving device is a filter, but it's not a membrane. To ease the differentiation between a filter and a membrane, we can go to conventions. So filters are generally limited to separation of particles that are larger than a micron. To illustrate the scale, a dust particle, the one that we cannot see with our naked eye, there are at least 5 microns. So we can say that membranes are filters for the invisible world. So membranes are filter for those that we cannot see with our naked eye. So what are the properties that a membrane can be selective with or for? First is size exclusion, or the molecular size. Second is through molecular interactions. So it may be the charge. So it refers to how charged species such as ions attract or repel each other. It could be group interactions, primarily hydrophobic or hydrophilic interactions. And then affinity, which may be the biospecific interactions among proteins. Moving on, as illustrated in the Venn diagram, we can see that membrane science is actually an interdisciplinary science. So it involves concepts from materials engineering, chemical engineering, as well as the biochemistry and biophysics. So in membrane science, the material engineering aspect refers to how to decide what materials to choose for the membrane, how to prepare the membrane from its base materials, and how to employ methods so that we can modify the membrane. This also includes several techniques to evaluate the membrane properties, from mechanical tests to advanced microscopy and spectroscopy. So you might be curious what interface science deals with. It actually deals with the study of colloids, such as emulsions, mainly. It also deals with the surface tension, adsorption, rheology, and other interfacial phenomena. So it is very useful when we apply membrane processes to food applications, since many of food are actually emulsions or colloids. So the biochemistry and the biophysics aspect, this small part arises from the study of the biological membranes, as well as the applications of membrane separation processes to biological systems. So biochemistry and biophysics aspect gives rise to biologically inspired membranes, as well as specific applications to biotechnology and the medical field. But where is chemical engineering and membrane science? chemical engineering intersects with membrane science along the fields of transport phenomena via the modeling of the transport mechanisms, especially the mass transport, in the fluid dynamics, especially in the device design of the actual membrane device that we use for the process, especially the geometry of this process, and then the process design on how the membrane process is actually integrated with other processes, how is it hybridized, or how can they be made into multi-stages. So chemical engineering is indispensable. It's very important for the current state of the membrane technology, especially in its applications in the industrial level. So chemical engineering is indispensable. So what are the types of membranes? So we can easily classify membranes based on their material. Technically speaking, membranes can either be synthetic or biological, but we are focusing on the synthetic ones. The synthetic types, the more industrially significant ones would be the polymeric membranes and the ceramic membranes. So in actual, polymeric membranes is the prevalent material for many commercial membranes due to their lower costs. And also, there's a wide array of polymers to which you can choose from to make your membranes. On the other hand, ceramic membranes are more of niche or specific applications because they have better stability than polymeric membranes, because ceramic membranes, they can withstand higher temperatures and other harsh conditions such as solvent. Besides ceramic membranes, there are also other inorganic membranes. They can be made up of carbon or metal, such as palladium. We can also classify membranes based on their structure. So in the simplest sense, membranes can be porous or dense. So porous membranes, these membranes have pores or they have holes. So we can say there are holes in which the components can flow through. On the other hand, as differentiate with dense membranes doesn't have these holes. So they can also be called non-porous membranes. So this leads to some interesting mass transport mechanism. So these are the types of membranes when we're referring to symmetric homogeneous membranes. However, when we add in modifications, we can actually obtain a membrane that is both porous and dense. So this is the case for integrally skinned asymmetric membranes, or ISAs, which have a dense skin layer. We can also combine two different materials and get a thin film composite, or TFCs. Or perhaps we may incorporate some nanoparticles and develop some mixed matrix membranes or thin film nanocomposites. So possibilities are endless, and the sky is the limit to membrane properties when we are considering these material engineering aspects. However, moving on to the more chemical engineering aspect, how exactly does a membrane process operate? So, as you can see, there will be three process streams. First of all, the feed, and then the retentate or concentrate, and then the permeate. The product in this membrane process can either be the retentate or the permeate, or in some cases, both of them are the product. In a membrane process, there are two key performance indicators that we need to know. So what are these key performance indicators? These are the permeability and the selectivity. So permeability, this quantifies how easily a component can pass through the membrane into the permeate side. So that is permeability. On the other hand, selectivity, it evaluates how much of a component is rejected into the retentate or concentrate. So that is selectivity. However, these indicators have a paradox. There's a paradox between permeability and selectivity. It means that At high permeability, it often leads to low selectivity, or vice versa. So knowing this trade-off is essential to a well-guided membrane selection for a chemical engineer. So if you need a highly permeable membrane for your process, you need to choose a membrane with high permeability. Or if you need to have high selectivity for your process, you need to choose a membrane with higher selectivity. You need to balance between these two performance indicators. So that is essential for selection of membrane as a chemical engineer. Next, we also need to know the different modes of operation using the membrane. So a membrane process can be operated in dead-end mode or cross-flow mode. So when we say dead-end mode, we can also call it normal flow mode. The feed stream flows through or directly through the membrane. So the good thing with a normal flow is that it is straightforward and it can be easily done in small scale, especially the laboratory scale when we are testing it in the lab. However, there is a limitations to this process, because as you go on with the membrane process, there is a build-up of materials on top of the membrane, and that is what we call fouling. And this build-up of materials on top of the membrane reduces the transport or reduces the flow of the component through the membrane. Thus, it is not good. So that's why we have another mode of operation, which is a cross-flow mode or tangential flow. In this mode, the feed stream flows parallel to the membrane. In this way, we reduce mass transfer limitations which arises from a normal flow. So with this, there is more turbulent regime on the side of the membrane so that we avoid concentration polarization, and also the fouling is reduced since the flow is not directly through the membrane. It is parallel to the membrane. As similar to other processes, a membrane process can also be operated in batch or continuous manner, such as batch process such as discontinuous diafiltration, or continuous manner such as a multi-stage membrane cascade. So we can apply it to liquid-liquid extraction. So we're moving on to the transport phenomena. So transport phenomena, in a general sense for chemical engineering concept, it involves the movement of mass, momentum, or energy through a medium. So the generalized concept, to make it easier or simpler for those who haven't encountered transport phenomena, is that it relates the flux with the driving force and resistance. So what's flux? Flux is the transfer rate of mass, momentum, or energy per unit area. So it says that the amount or the rate of transfer of mass, momentum, of energy is directly proportional to how much driving force you apply to the process, and it is indirectly proportional it's inversely proportional to the amount of resistance to the flux. So it just means that the higher the driving force we apply for a process, the higher will be the transfer rate or flux. So what are the driving force that we can use or apply for a membrane process? So we have 4 different driving force that we can apply. It could be a pressure gradient. It could be an activity gradient, which you may be more familiar with the concentration gradient. It can also be expressed in partial pressures, water activity, osmotic pressure. And then we can also have the application of electrical field. And fourth, we can have temperature gradient. But most of the time, the driving force for membrane processes are pressure and activity gradient. So how can we understand the transport through the membrane. So we can understand them through some transport model. So the simplest ones will be the four-flow model and the solution diffusion model. So the four-flow model, we apply this model when we are talking about porous membranes or the membranes with the holes. So the pores or the holes, we assume them to be like cylindrical pipes. So we assume them to be like cylindrical pipes. So for the solution diffusion model, on the other hand, we apply this for the dense membranes or those without pores. So what we assume for solution diffusion model is that the membrane process or the transport of the component through the membrane occurs in 3 steps. So unlike the four-flow model, which just flow through the pores to the other side of the permeate, in the solution diffusion model, there's 3 steps. First is the adsorption of the component into the membrane. Second is the diffusion of the component through the membrane. And then lastly, the desorption of the component out of the membrane and into the permeate side. So that is the assumption for a solution diffusion model. So what would be the equation that we'll be applying? So for a four-flow model, we apply a Darcy's law, which describes the fluid flow through a porous medium. Whereas for a solution diffusion model, we apply Fick's law, which describes mass transport from higher concentration to lower concentration region. So you have in Fick's law, we assume for the solution diffusion model that the adsorption and the desorption process are very fast or instantaneous. So as we look into the pressure gradient that is considered in each model, for the four-flow model, the driving force that we consider is actually the pressure gradient. Whereas for the solution diffusion model, it is the concentration gradient. So these models are a very good way to understand what actually happens in the membrane process. So these are the basic membrane transport theories that we are discussing in order to understand the transport phenomena for the membrane process. Now we are moving to how they look like in actual. So how are membranes designed in actual? So they are designed into modules. So they are designed in modular formats. So these are the compact units that may contain one of up to 5,000 different membranes. So individual membranes. So you can have one individual membrane or 5,000 individual membrane. So the modules, they can be configured as flat sheet or tubular. So what is important in the design of this module is that they consider for desirable fluid dynamics within this module. So it is highly considered in the design. So what do we want to promote? We want to promote turbulence inside. We want to avoid dead zones inside the modules. And also we want to reduce mass transfer limitations. So most of the time, as we have discussed earlier, we obtain this desirable fluid dynamics by using cross-flow operation. So most of the time, these modules are designed for cross-flow operations. So it's because of the better hydrodynamics as compared to a dead-end operation. So we're going to discuss flat sheet membrane modules. So there are 2 types of flat sheet membrane modules, a plate and frame type and a spiral wound type. So as you move from left to right, you're increasing compactness. So a spiral wound is more compact than the plate and frame module. However, the advantage of a plate and frame module is that it can be applied to different processes, and it can be these processes can be driven by pressure, it can be driven by concentration or by an electrical field. So plate and frame module is very, very versatile. However, spiral wound module is compact. It means it can have a lot of membranes inside. So most of the time and most of the most of the commercial membranes that you would encounter in an actual plant would be spiral wound type. These are the most commercialized ones. Spiral wound type has big relevance to industrial water treatment, so that's why you will encounter more of spiral wound module types for the flat sheet membrane modules in the industry, such as water treatment, in the preparation of processed water, and several other process applications. When we go to the tubular configuration for the membrane modules, you can have tubular type, capillary type, or hollow fiber type. So as you move from left to right, from tubular to hollow fiber, you increase the number of tubes inside the module, but you also decrease the tube size. So you have bigger tube size in a tubular membrane module and very, very small tube size in hollow fiber module. The drawback with the small tube size is that as you go from a bigger tube size to a smaller tube size, you reduce the operating pressure, because as we know, if the tube is much smaller, it can only withstand also lower pressures before it ruptures. So that's the catch. You can have bigger tubes but lower number, so you have smaller surface area, but you can have many small tubes with have higher surface area, but you can only operate with a lower pressure. So there is a paradox again. So we are now going to discuss what is the advantages of a membrane process. So a membrane process has high selectivity. This can be traced back to the mode of separation, since it occurs on a molecular scale. So you can say that a membrane process is versatile. It can be tailor-fit to systems, possibly due to variety of materials for the choice of the membrane, and also the variation in the membrane process design. So it's versatile. Due to the molecular scale separation, it results in high selectivity. There's no phase change. In most of the membrane process, there are no phase change, but there are some exceptions. So because there's no phase change, so there could be less energy requirement, because this phase change that is related to heating or cooling, this would be the one considered for this. So there is less energy requirement. And third, modular design, which we discussed earlier, those modular format. Because of this modular design, they are easy to install into the process. They're much easier to operate, and there is much less complex maintenance. So the modular designs also enable for smaller footprint in the plant. It means that this membrane device or modules, they take up very much smaller space in the plant. So if you are designing a plant and you only have small area, and you consider for a choice of process, membrane process would be really advantageous, since they require only a small area for the same throughput or same capacity. And since the membrane process has no moving parts, so generally the operation and the maintenance, as well as the process control, they will be less complex. Next, they are more economical. So how can I say that membrane process is more economical? Because they enable the recovery of more valuable products, which may be found in smaller concentrations in the process stream. So you are able to recover more value from your process stream. And in that way, you reduce the undesirable byproducts that you produce, as well as you promote process recycling, and then you avoid wastes in the process. So that makes it more economical because of that that capability to extract or obtain these minor components from your process stream. And then fifth is that a membrane process is more environmental. So when we say more environmental, it refers to the energy efficiency due to the less energy requirement and the less use of chemicals. Since in a general process, membrane process, you don't apply much chemicals into the process. However, these advantages, they can have also drawbacks, and this leads to the disadvantages of the membrane process. So, as we can see, membrane process, they can be tailor-fit to different systems, and thus they need re-optimization for new systems. So that's a bad thing. So certain membrane, there is not a membrane that is available for every application. So you might need to optimize due to the temperature, to the pressure, or incompatibility with the chemical. So considering that many of the commercial membranes are polymeric ones, which are limited to the temperature, the range of temperatures to which they can be applied, or the solvent to which they can be applied, then that requires optimization for the process. So you might need to adjust process streams in order to apply a membrane process. Second disadvantage, since there's no phase change, it might require large energy for pressurization. So you need to pressurize the feed stream so that they will pass through the membrane. And for a feed stream with a high salt concentration, that will be very, very high pressure. And this is the case for desalination processes. Third, since it's modular, the scale up is only linear. So what do you mean by linear? For example, when you say linear scale up, the scale up is additive. You cannot just create a membrane process that is much bigger. You need to add units. For example, you can only add units in order to accommodate a bigger and increased process input. To illustrate, if the feed volume is increased 10 times, you cannot just create a membrane that is 9 times bigger to accommodate the extra volume. You would need 9 additional units. So that's what you mean by linear scale up. You cannot create a bigger process. You need to add individual processes if you increase your input. So that's one disadvantage. And also the transport, for some cases it might be complicated. So the modeling, it may be very hard for process control application. More economical. So membrane process, they need to be optimized for membrane area and the pump. So you can have more membranes or large membrane area and then small number of pumps to process a certain input of components, or you will have small membrane area but large number of pumps. So you need to find the optimum for these two process parameter so that your membrane process will be economical. And also, you need to consider the costs for pre-treatment or post-treatment, if any, if it is required for your process. So it's not, a membrane process is not directly more economical than other process. You need to consider a certain process versus a membrane process and consider everything, especially their disadvantages. And the fifth one is that it may not be that environmental friendly. So it might not be ecologically friendly as what we thought for the process, since in a life cycle analysis, we could actually consider the membrane, how it was made. And the manufacturing of a membrane is not that ecologically friendly at all, since it it uses some chemicals, solvents, and it might be energy intensive for some applications. So, as we can see, a membrane process is not directly more economical or more environmental compared to other processes. You need to consider many things, and you have to be knowledgeable about the membrane process to make the most out of it. And whether the membrane process will be economical, it depends on how it is integrated with other processes and how knowledgeable the process owner is with the membrane maintenance, so you avoid unnecessary replacement of membranes. So also, it's not that environmental if you consider everything that is used up in making up the membranes. As we said, the energy, the solvents, and also the pollutions or the effluents produced in the making of the membrane process. They all have to be considered. So, for a chemical engineer, we must always think whether a membrane process is applicable for a certain application. So we need to consider the chemistry as well as the technical considerations, especially with the process conditions, the temperature and the pressure, and then also whether it will be economical for the process, or what are the benefits of the applications. So we need to balance, or we need to measure up, will it be beneficial or will it not be not beneficial. So we decide it based on technical values and economic value. So how to classify membrane processes? So we can classify membrane separation processes based on their driving force and the nature of the process. So they can be pressure-driven processes, they could be activity-driven processes, electromembrane processes, temperature-driven processes, and reactive processes. And in the discussion, we will not be discussing biological membranes or processes involved in biological membranes. So we'll start with the pressure-driven processes. So the pressure-driven processes involves and includes microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So these are the more widely known membrane separation processes. And aside from microfiltration, this ultrafiltration and reverse osmosis down to reverse osmosis must be differentiated with typical filtration. Microfiltration, they function just like a filter, but the rest is entirely different. They function more of as a membrane. So, as you can see from this diagram, they are filtering for different components. For example, in microfiltration, they can filter bigger components, whereas if you go to reverse osmosis, they can filter up to the ions. So, if we look into the membranes, types of membranes applied to this process, we can see that porous membranes are applied for the microfiltration and ultrafiltration processes, whereas dense membranes is applied for reverse osmosis, and then both types of porous and dense membranes are applied for nanofiltration membranes. So we go to microfiltration. So in microfiltration, they are able to reject particles or components with size of 0.1 to 10 microns. These components generally are particulates, colloids, and bacteria. So as you can see, this one. This microfiltration process is very essential for its sterile filtration, the pre-treatment for processed water and wastewater. So it is very important. It is applied to ensuring that the air and the growth media in bioreactor are sterile. So there is a use for sterile filtration, and also for medical applications to ensure that the environmental air in a certain medical facilities are sterile. So you avoid contamination from microbes and other unwanted microbiological organisms. So microfiltration, so microbes, they filter microbes. So our particulates bigger than the size of microbes. So we move to ultrafiltration. So for ultrafiltration, they can filter out or they can reject particles that are with the size of 0.01 to 1 micron. So these are actually invisible to our naked eye, these particles. Or we can also say that the ultrafiltration process can filter out materials or components with molecular weight that is 10 to the 3 to 10 to the 6 daltons or grams per mole. So most of these components would be proteins and polysaccharides or complex molecular structure such as DNA. So since ultrafiltration is quite more costlier than microfiltration. So ultrafiltration can only be economical when it involves heat in product recovery and water recovery, and when you are able to avoid additional treatment costs for the wastes. So you apply ultrafiltration in the process. So what are the industrial applications to which it is involved? So clarification of juice. So clarification of the apple juice or orange juice. Concentration of whey for the dairy industry. Diafiltration of protein, which you want to purify in several biotechnologies. Resource recovery and recycling for oils and paint, water use and water treatment. So you can see, these are all about recovering something, recovering product, heat, or water or energy. So that is the only way to make ultrafiltration economical. So there's another specific application of microfiltration and ultrafiltration membranes, which is the membrane bioreactor. So this is when these membranes are applied in activated sludge process of biological wastewater treatment. So they can be submerged inside the bioreactor or external out of the bioreactor. So membrane bioreactor process, they combined the treatment and the separation process. So in doing so, it allows for a more compact process. So it's more compact. So it removes the need for the building of clarifiers. So if you need a wastewater treatment facility, a biological that works on a biological process, and you don't have a lot of area for your plant to build a clarifiers, secondary or primary clarifier, then you may think of a membrane bioreactor, since it can be used for smaller area. It has a smaller footprint for a plant design. And also, since the organic biomass is returned into the membrane bioreactor, there is higher concentration for the biomass, and thus the water quality that comes out mostly is much better than the typical biological wastewater treatment process using activated sludge. So this membrane bioreactor can be applied both to an aerobic process and anaerobic process. So they can be applied to biological wastewater treatment, whether it's aerobic or anaerobic. Now moving forward to nanofiltration. Nanofiltration can filter particles with the size of 1 to 2 nanometers, and most of the time this refers to multivalent ions or monovalent ions. So these multivalent ions or divalent ions typically are the calcium and the magnesium ion in water, which constitute the hardness in water. So most of the greatest application of nanofiltration would be in the water softening or the removal of hardness from the water. And so generally it's applied to water treatment also, when you want to produce softened water or drinking water. And it can also be applied to organic solvent nanofiltration. So it's quite different, since most of the processes for membrane process are employing aqueous streams. So membrane process which operates with organic solvent is a different one. It has been applied to processes in petroleum industries, for the lube oil dewaxing and the refining of naphtha, or for several biorefinery, for the production of biodiesel, for the recovery of solvents, for the production of the vegetable oil, recovery of the hexane solvent used for the extraction of oil from the nuts or different other vegetables. So as compared to the ultrafiltration and the microfiltration process, so it has a very, very small size of components which it can reject. So these nanofiltration membranes are now employing dense membranes, including porous membranes. So that's the difference between the nanofiltration and the other types of membrane process we discussed earlier. And then moving on to the reverse osmosis or RO process. Once upon a time, people called the reverse osmosis process as hyperfiltration, perhaps because it exceeded what their notions of the limits of filtration could be at the time. But reverse osmosis stood out as a more apt name or appropriate name for the process, since it describes the process better, or it describes what actually happens with the process better. So pressure must be applied in a reverse osmosis process. Large pressure must be applied to exceed the osmotic pressure of the water towards the brine. So in a normal osmosis process, as we can say, if there's a membrane separating the brine with a higher concentration of salt and water, the water will flow towards the brine. So that is the normal osmosis process. But since this is a reverse osmosis process, you apply pressure to counteract the osmotic pressure between the brine and the water, so that what actually happens is that the water flows from the brine into the other side, in the permeate side, towards the purer water. So this pressure might be higher than 27 bars, or double 27 bars, because typically seawater has an osmotic pressure of 27 bars. So the pressure applied must be around 60 bars or more. So this application of pressure results to the reverse osmosis process. So definitely it's not your typical filtration process. In terms of application, RO or reverse osmosis has taken over the world, generally for the desalination processes. Around 80% of the desalination plants in the world is operating with a reverse osmosis process. I may consider this because most of these plants are small scale plants. So most of the application with membrane process is for small scale plants. And currently, this 80% of desalination plant can provide to 50% of the total volume of desalinated water worldwide. So this is where membrane processes are getting bigger industrial applications in terms of the desalination process. So desalination process can be applied for seawater or can be applied for brackish water. So what is brackish water? Brackish water is the combination of the seawater and the river water. So this is the part where the river meets the sea. So you will have brackish water there. There are some salt concentration in brackish water. Reverse osmosis can be used for drinking water treatment, and also for production of ultra pure water. This ultra pure water is essential for several manufacturing industries, especially semiconductor ones, those that require the water to be not contaminated with any microbial or without any trace of hardness. So ultra pure water production is mostly done with reverse osmosis process. So quite a trivia. That's something that you might not actually do. But have you ever thought about drinking water from your toilet? So it's something that you might not think of doing, but with reverse osmosis is actually possible. And in Singapore, they have this toilet to top bottled water, which you can buy from the stores, and then without, if you're not aware, you might you might not you might think that it's not is actually the water from the toilet that you're drinking. When you're drinking this bottled water, you're actually drinking the water from the toilet, but molecularly, yes, they're the same, but without the contamination from the actual toilet water. So with reverse osmosis, they're able to eliminate all of those contamination and make the water drinkable. So reverse osmosis is actually one of the mature technology amongst other membrane processes, and it is continually growing and developing. So there's still future aspects for reverse osmosis, and it's now looking forward on the biologically inspired membranes, aquaporin membranes, and some advances in nanotechnology with graphene membranes, which are made of carbon-based membranes. So moving forward to activity-driven processes. So activity-driven processes, there are three basic types. It could be membrane contactors, gas separation process, or evaporation process. For the membrane contactors, it could be liquid-liquid contactors, depending on the phase of particle of the feed streams, or gas-liquid contactors. So this activity-driven process can have different driving force. So for liquid-liquid conductors, it could be concentration, it could be water activity or osmotic pressure gradient. For the gas separation and evaporation process, it could be the partial pressure gradient. So what are the advantages of these activity-driven processes, membrane processes specifically? They're generally more compact than their typical counterpart. They have higher specific area as compared to, say, a typical gas absorption column. So they also don't have flow limits. There are no flooding limits or bubbling limits. There's no phase mixing, so the phases are separate. So you don't need to consider for the difference intensity of the liquids or whether they are miscible or immiscible. So those are the advantages of these activity-driven processes. And most of the time, they're operating in hollow fiber module or device design, since hollow fiber device design offers the biggest surface area for the process. So in the types of membranes that are used for these processes, for the membrane conductors, they often use porous membranes. For the for evaporation, it would be dense membranes. For evaporation and forward osmosis, it's dense membranes. And for the gas separation, they consider both porous and dense membranes. So going for liquid-liquid membrane conductors, the processes under this type is the liquid-liquid extraction, forward osmosis, and membrane emulsification. So discussing for liquid-liquid extractions, so when you have two liquids and you want to extract components from one phase to another, then you apply them using a liquid-liquid membrane conductor. You use this type of membrane process. So what are the industrial applications with liquid-liquid membrane conductor? So using membranes as a conductor enables you to recover specialty chemicals, or recover some contaminants from your wastewater. For example, the recovery of metals or organics from effluents is enabled by liquid-liquid extraction by a membrane conductor. And also you can recover the fermentation products from your bioreactor or other organics, or you can do racemic resolution for pharmaceutical applications. So these are very specialty or niche extraction processes that are enabled using liquid-liquid extraction via membrane conductor. So moving on to forward osmosis. In a forward osmosis, it is the same as the typical osmosis process. But in this process, you employ a draw solution, which is this green part, which has higher concentration, to actually induce the water flow from the feed out of the feed to the draw solution. So you are actually inducing osmosis. But the difference with typical osmosis is that in a forward osmosis process, or forward osmosis membrane process, you regenerate your draw solution. So there's regeneration process for the draw solution. It could be done by evaporation or some other less economically or energy efficient process. So for a forward osmosis to be economical, there are several things that we need to consider, which is the regeneration step. So forward osmosis process can be applied for osmotic evaporation, or can be applied for membrane crystallization, which allows for controlled high precision crystals as differentiated with other types of crystallization. So this is more for a pharmaceutical application. So the general application of this forward osmosis in industry is specifically for volume reduction. If you want to reduce the volume of your feed stream, especially if your feed stream is waste or liquid waste, so you reduce the volume of water, you extract them using the draw solution, and then regenerate the draw solution to extract more of the water out of your wastewater or your feed. So it can also be used for concentration of heat sensitive products. So since it doesn't apply any heat in order to concentrate, so it is applied for dairy concentration, for the milk, for the food, such as juices, and also for pharmaceutical products. So if you are transporting your products for long distances, then a forward osmosis process will be beneficial to reduce the volume of the product that you are transporting. Some unique hybridization of forward osmosis process is hybridizing the forward osmosis with the reverse osmosis process with the seawater. So in this process, the draw solution that you use is actually the seawater that you will be feeding into the reverse osmosis process. So when you use the seawater as a draw solution, you extract the water from the wastewater, and then this seawater, the concentration of the salt in the seawater is diluted because of the water from the wastewater, and then this diluted seawater is then fed into the reverse osmosis process, and with that you will be needing lower pressures, since you have technically lower salt concentration. So that is one unique hybridization of this process. Then moving forward, membrane emulsification. So a membrane emulsification process still employs liquid-liquid membrane conductor, but the difference is that it employs pressure gradient, so that the flow of the components happen. So this membrane emulsification process enables the creation of well-sized or precisely sized emulsion droplets into the other phase without the need for the emulsifier. So as you can see, the first phase, say the blue phase, liquid phase, is pushed through the membrane because of the pressure gradient and because of the velocity of the the velocity in the other phase, in this light phase, light liquid phase, the blue liquid phase is detached into small emulsion droplets. So they're detached into small droplets within the other phase. So this is applied when you want to do water and oil in water emulsions. It means that you produce a droplet within a droplet within a droplet. So that is the simplest explanation for the water in oil in water emulsion. So you can see that the light blue ones could be the water droplets. These dark blue ones is the oil droplets, the bigger oil droplets, and then this phase, the white liquid, the other phase in the permeate is another aqueous phase or water phase. So water in oil and water phase. So water in oil and water emulsion. So, however, this process is currently limited in small-scale industrial application. So, it's very niche application for producing certain emulsions, and specifically, these are applied for encapsulations of functional agents for food, for drugs, and other shear sensitive products. So, generally, it applies to food, biotech, and pharmaceutical industries, this type of process. So we're moving to the gas-liquid membrane contactor. So main application of gas-liquid membrane contactor is in terms of gas absorption or stripping. So the advantage of a membrane contactor process is that it allows simultaneous degassing and bubbling. So it allows the removal and the addition of a gas simultaneously. So generally it has been useful for beverage industries which needs the addition or removal of gas. For example, if for a beer product which requires to be deoxygenated or removal of oxygen and also to be carbonated, so this process can be done simultaneously using a gas-liquid membrane contactor. So other applications to which you can apply a gas-liquid membrane contactor is the aeration of water in utilities, so you avoid the corrosion of a process, especially when you're producing steam, and the removal of ammonia from wastewater, carbon capture from flue gas, or the sweetening of natural gas when you remove CO2 or hydrogen sulfide, or you remove water components from your natural gas. So, but the main application for a gas-liquid membrane contactor will be in beverage industries, as well as in water deaeration, in several utilities. Utilities such as boilers, such as cooling towers, and steam production. So generally, those types of utilities. And then we'll move to membranes in regenerative medicine. So membrane contactors, they're not limited to applications in industrial setup. So they can be also applied in a medical setup in terms of regenerative medicines. For example, dialysis. The dialysis units that we hear from the hospitals are actually membrane processes in action. So hemodialysis process or the artificial kidney is a membrane contactor process in which there's two feed stream, the blood and the dialysis feed stream, and then through the filter or through the membrane filter, the contamination, the metabolites from the blood are transported into the dialysate so that you're able to perform the functions of a kidney. So also another membrane application in regenerative medicine is the use of membrane blood oxygenator, or what we call the artificial lungs. So where is the artificial lungs used? When you hear about a bypass operation or heart surgery, that is where you use a membrane blood oxygenator, since you need to simulate the breathing or the oxygenation process in the body without the lungs, since you're operating with the heart. So how is it important in a bypass operation? you can say it's important because of the cost. It costs around 1/3 of an actual bypass operation. So the cost of a bypass operation, heart operation, 1/3 of that is just due to the use of a membrane blood oxygenator. So this is a quite costly process. So if we looked further into these two different processes, we can see that a dialysis process is actually a liquid-liquid membrane contactor, whereas the membrane blood oxygenator is a gas-liquid membrane contactor. And the liquid in this case is the blood of the patient. So besides these two medical applications, there's also developing process or developing membrane applications in the form of bioartificial pancreas, in which pancreatic cells which produces insulin are encapsulated in membranes. Or the fourth one is the use of tissue scaffolds for tissue engineering. So these tissue scaffolds, you can say that they are just the support to which the cells are growing. So they functions like a cell membrane. They allow the food or the nutrients to come in, nutrients and oxygen to come in, and then the metabolites and the CO2 to come out. So they enable the growth of tissue in the lab for tissue engineering. So these are used for creating organs from stem cells. And other applications of membrane process would be into drug delivery functions. So membrane processes, as we can see, is not limited to industrial application, but also applied to medical processes. Now, moving forward to gas separation. So gas separation allows the separation of gases based on their molecular weight and or their affinity to membrane material. So they can be applied for several applications, primarily for carbon capture. So in this carbon capture, they can be applied to flue gas or to natural gas. They can also be applied for gas scrubbing when you remove SOx and NOx from your flue gas sweetening and dehydration for the natural gas when you remove sulfides and water. And then you can also use gas separation membranes in order to produce nitrogen or oxygen streams when you want to enrich them into certain concentration but not that pure. And then you can also apply this process for production of hydrogen from ammonia. For example, in this process, which is illustrated here, the decomposed ammonia is the feed in this process, and then the retentate goes straight through, but the hydrogen molecules, they are adsorbed on the membrane, diffuse through the membrane, and then desorb to the permeate side, and that's how you obtain a pure hydrogen from the process. So this process, as we can say, is a solution diffusion model process. So this process specifically uses a dense membrane, but as we know, gas separation process employs both porous and dense membranes. These applications for gas separations are available not only in pilot scale, but also in the small industrial scale. Pervaporation is another activity-driven process. In the pervaporation process, it employs hydrophilic or hydrophobic membrane to concentrate the dilute volatiles at mild conditions. So it gives importance whether the membrane is hydrophilic or hydrophobic, since it determines what volatiles goes through the membrane. So as we can see, if it's a hydrophilic pervaporation, which uses hydrophilic membranes, then the dilute water will be able to pass through the membrane. Whereas if it's hydrophobic for evaporation process, then the dilute organics, for example in water, will be able to pass through the membrane. So in this process, it is driven by partial pressure, as we have discussed in the earlier part. Partial pressure in this in the permeate side is maintained by using a vacuum so that the gradient is continuous. When the feed stream in this process is in gas phase, then we call this process vapor permeation. And one must take note that, again, a membrane process is not a thermodynamic process. It is a kinetic process. It's a rate-based process. Therefore, it is able to bypass equilibrium. So, a evaporation process can bypass phase equilibrium limits that are encountered in a typical distillation process, and enables the crossing of the azeotrope, which in distillation process limits the concentration to which you can obtain your distillate, the purity of your distillate. So the application of evaporation process generally and currently is applied to concentration of heat-sensitive organics. So when you have heat-sensitive organics in that is very dilute, you can concentrate them using evaporation process. You can also apply them for monomer recovery in petroleum process, and especially for alcohol and solvent dehydration. As we know that there is an ethanol water azeotrope. So this azeotrope is able to be bypassed by a evaporation process. So moving on to the other types of membrane separation process, which are the electromembrane processes. So the major distinguishing characteristic of all electromembrane processes is that they all employ ion exchange membranes. So ion exchange membranes can either be a cation exchange membrane or an anion exchange membrane. When we say cation exchange membrane, then these membranes have negative charges and they allow cations to pass through and they reject anions. Whereas an anion exchange membranes, they contain positive charges, and these positive charges allow negative ions to pass through and they repel the positive ions. So those are the differences. So electromembrane processes are currently employed for chemical production, purification, and power generation process. So for chemical production process, there is membrane electrolysis. For purification processes, it will be the dialysis processes. And for power generation aspect, it will be the use of fuel cells and the reverse electrodialysis process. For the membrane electrolysis, membrane electrolysis process, it allows for the simultaneous electrode reaction and the separation of the electrolysis product. So it's a combined process. So you perform an electrolytic reaction and the products of these electrolytic reactions are again separated at once. So it enables you to have two product streams from your feed stream. So a chlor-alkali process, for example, which is illustrated here, enables the production of Cl2 gas or the chlorine gas and NaOH or caustic soda from brine. So from brine, they are able to produce two products. So in this process, the ion exchange membrane, as you can see, performs three functions. It insulates the electrodes, it conducts the protons, the positively charged ions, and it separates the two product streams. So it has three function. And in this way, it avoids the unwanted byproducts that you might get if you don't have proper separation of the product streams. So other applications for membrane electrolysis would be production of hydrogen via water electrolysis, and also production of oxidative agents for water disinfection. When we go to electrodialysis, in electrodialysis membrane process, you apply an electric field on the separate ends of the membranes, and these electric fields causes the transport of ions from the feed stream. So if you have a feed stream here, the positive ions goes through towards the anode, while the negative ions goes towards the cathode. And in this way, in the feed stream, the ions are removed. An electrodialysis setup is comprised, as you can see, of several layers of an ion exchange membrane and cation exchange membrane. As you know, cation exchange membrane will not allow the transport of negative ions, while an ion exchange membranes will not allow the transport of positive ions. And in this way, they're able to obtain a permeate which is free of these ions. If this electrodialysis process is hybridized with an ion exchange resin bed, then this is known as electrodeionization process. So many of the semiconductor manufacturing industries, they employ this electrodeionization process in order to obtain their ultra pure water for the cleaning of the products from semiconductor. So electrodialysis is currently the cost-effective method in desalination of the brackish water. Since brackish water have lower salt concentration, electrodialysis is better, or it's already a competitive process over reverse osmosis. It can also be used for water reuse, drinking water treatment, as well as the acidification of beverages, since acids are technically ions. They have ions. So they are able to be separated using an electrodialysis process. So what is the disadvantage of the electrodialysis process? The disadvantage is that when you have neutral contaminants in your feed, then they won't be affected by the electric field that you will be applying. So you have this feed with the ions goes through the cation or anion exchange membranes, and then they go out into the concentrate, and then the feed stream, which is removed with ions, will now be the permeate, which have lesser ions and much more pure water. Now moving to the Donan dialysis process. In Donan dialysis process, it employs concentration gradient. So it's another exception for the electromembrane process. It applies zero electric field, so there's no electric field. And the difference with this process compared to other dialysis processes is that you need to consider the charge balance to drive the desired diffusion of the ions. So charge balance, as we know, that in both streams there must be a balance of charges. So, for example, if a negative ion goes through the membrane, then a positive ion must also go through the membrane in the same way, so that the charges are balanced. Okay, so typical application of adonan dialysis process is that it is applied for recycling of acids. So in this recycling of acid, they employ an anionic exchange membrane. So in this way, the anions are able to pass through the membrane. For example, if you have hydrochloric acid, the chlorides were able to pass through the membrane, and as the chlorides pass through the membrane, they require positive charge to also pass through them, so that the charge is balanced, so the hydrogen ions also passes through the membrane. However, if you have metal ions which have higher valence than 1 or higher valence than the protonated hydrogen ion, then they are rejected, since by concept of charge balance, they will require much greater driving force in order to pass through this anionic exchange membrane. So they can also be applied for wastewater treatment when you want to remove charged toxins from the wastewater. And they can also be used for water softening. So what is the disadvantage of this process? First of all, this is a concentration gradient process. So concentration gradient driven process, and therefore it is this one is limited by equilibrium. So unlike typical membrane process, this one is the one that is limited by equilibrium. And also, if the toxins from the wastewater is not charged, then you are not able to remove them using this dialysis process. Now moving on to power production using the electromembrane process. The reverse electrodialysis is actually a reverse of the electrodialysis process. In this case, you actually tap into the salinity gradient from the feed streams in this process. So you tap into the salinity gradient, or what we call the blue energy, between a feed of low concentration and a feed of high concentration solution. And because of the transport of ions from the high concentration solution to the low concentration solution, the electrons are forced to move through this two electrode, and in this way it generates electricity. So what is the application of reverse electrodialysis? So you can generate power by mixing in or using river water, which has lower salt concentration or ion concentration, and then seawater, which has higher salt concentration or ion concentration. In this way, you're generating electricity due to the osmotic difference between these two feed streams. So currently, there is a pilot scale level of plants for reverse electrodialysis, mainly in the Netherlands, and it is still working and on process. So as we can see, it's the chemical potential that generates the voltage across the ion exchange membranes, and then this voltage difference, this is the one that drives the electrons. So that is how a reverse electrodialysis process works. And then going to much more known process for electromembrane process, which are the fuel cells. So specifically PEM fuel cells, or polymer electrolyte membrane fuel cells. So in a fuel cell, it employs hydrogen as fuel in order to generate electricity. So the hydrogen gas, as they fuse to their catalyst, they're separated into the protonated hydrogen, which are able to pass through the membrane to the proton exchange membrane. So since it's only the hydrogen ion that is able to pass through this membrane, then the electrons needs to travel through the other pathway. And in this way, there is the flow of electrons which produces the electricity. And then in order to maintain this process ongoing, there must be a continuous supply of oxygen from air. And in this way, this process only produces water vapor as the exhaust. So that is how the polymer electrolyte membrane fuel cells work. So this only allows for the hydrogen ion to pass through, but not the hydrogen gas. So this is how the membrane process separates in these fuel cells. Currently, fuel cells are available already in pilot scale applications, and they're mostly eyed for portable applications. So fuel cells are mainly tested for transportation processes, for cars, airplanes, spacecrafts. So this might be useful in the future, hopefully, as we move more into greener or alternative energy. Now, moving forward to the temperature-driven process, and the only temperature-driven membrane process is membrane distillation. So, in membrane distillation, they employ the vapor pressure difference generated from the temperature gradient from a hot feed and a cooled permeate. So you have a hot feed and then you have a cooled permeate, and then it's only the water vapor that's able to pass through the membrane, and in that way you generate a vapor pressure difference. But technically, it's a temperature gradient that creates this transport process. Since this membrane distillation process, and it's in this way you obtain water, pure water, it operates at a lower operating pressure and temperature. Therefore, it requires less energy. However, due to its low flux, it has a low flux at the current state of technology. The process is not that applicable for big industrial scale, and thus it is more economical when it's applied using solar energy or waste heat in the desalination process. So that is the most economical option for this process, and currently it's limited to pilot scale applications, and this technology is still in developing stage. On the next membrane process would be the membrane process which entails chemical reactions or the reactive processes. So it is the packed bed membrane reactor or PBMR, or we may call it catalytic membrane reactor if the catalysts are embedded within the membrane. So technically, this membrane reactor or packed bed membrane reactor is applied to reactions which uses catalysts or catalyzed reactions. In this process, you combine the reaction and the separation process in a one stage. So you combine unit operation and unit process in one step, and then the membrane in this process will provide you three functions. First, it can allow you to selectively extract the products. So you can allow the selective extraction of your products that you desire. It can also allow you to have controlled addition of the reactants because of the membrane, and also it can also act as a support or the way of retention or retaining the catalyst, so you do not lose your catalyst during the reaction in the reactor. So what is the advantage of a packed bed membrane reactor? This type of reactor, it overcomes the thermodynamic limits of equilibrium conversion. So this enables you to exceed the conversion that you might obtain for a given reaction. So as we say, as earlier, membrane processes are generally kinetic processes. They're not thermodynamic processes. Therefore, they can exceed equilibrium conditions. So this is ideal, especially when your reaction systems are limited by equilibrium, and most of them would be endothermic reactions. So equilibrium limited endothermic reactions would be favorable for a packed bed membrane reactor. And one of those reactions would be the production of hydrogen from methane. So in this process, it employs dense palladium membranes in order to obtain pure hydrogen from this reaction. So that would be the discussion. And to sum up our discussion for this lecture, we have the learning summary. So we learned today that a membrane is a selective semi-permeable barrier, and in membrane science, chemical engineering concepts on transport phenomena, fluid dynamics, and process design are important. Second, the transport phenomena of membrane process can be understood through the pore flow model and the solution diffusion models. And third, lastly, we are able to appreciate membrane separation processes, which are classified as pressure-driven, activity-driven, or concentration-driven, electromembrane processes, temperature-driven processes, and reactive process. The application of these membrane separation processes, they range from water treatment to carbon capture to power generation. And if you would be further reading on this membrane technology topics, I would suggest looking into Perry's handbook, especially the alternative separation processes section. You can also look with McCabe when you're looking into liquid membrane contactor processes, or John Copley's when you're looking for dialysis topics. You can also look for Fogler for the catalytic membrane reactor. And if you're looking into the generalized membrane topics, you may consult Baker and Mulder for student-friendly explanation of membrane separation processes. So that's it for the first lecture, and I hope you learned something in this introduction to membrane technology, and you appreciate some basic insights into the membrane technology, how it can benefit a chemical engineer, and what is the wisest way in order to employ membrane process. So as a chemical engineer, I think the use of membrane process must be a well thought of decision. So thank you for listening to this lecture.